All right, so let's get started. So hi everyone, my name is Rene. I'm a software engineer and I started to use Vaadin roughly 8 years ago. And yes, since then I mainly used Vaadin for building business web apps and internal tools. And around 7 years ago, I attended at the Vaadin Dev Days in Hamburg, and it was my first Vaadin event. And this was actually the only giveaway I was brave enough to take with me. And I still have it, and I will keep it because I like the claim, and I'm a little Vaadin fan, to be honest. And as I'm also a fan of React, I started exploring and using Hilla around a year ago. And because I'm also interested in things like DevOps and SRE, I had a chat with Marcus about a talk at a Vaadin Create conference. And yes, that's why I'm here today, actually. So I think we all heard a lot about Hilla yesterday, and I hope you all have a good understanding how to develop full-stack web apps using Hilla, because today I want to focus on building, deploying, and observing Hilla apps. And before I start, I would like to highlight some of Hilla's unique characteristics that will be important as we proceed. When we think about observability, it is important to keep in mind that a Hilla app consists of a React frontend and a Spring Boot backend. I'm aware that there are other options for frontend and backend, but for today we will just focus on React and Spring Boot. A Hilla app can be compiled to a native image using GraalVM, which brings us many advantages, and we will keep that in mind when we build our Hilla app for production. And last but not least, a Hilla app is stateless by default, which means it can scale very well, and this will allow us to choose a suitable deployment model for our app. But let's get started at the beginning. Let's assume we built this new and shiny Hilla app that our customers or colleagues are waiting for, and we want to push it to production. And there is actually a recommended way how to build a Hilla app that is about to be shipped to production, and this way is called the production build. So every Hilla app can be built as a production-ready artifact with the help of a corresponding configuration profile. And if we created our Hilla app, for example, at start.vaadin.com or using the Vaadin CLI, all the required configuration to create such a production build is already in place for us. This means to create a production build of our Hilla app, we just have to run this simple Maven command that you, I think, already seen during the conference. So what is actually happening during a production build? Well, the Java code of our Spring Boot backend will be compiled, of course. But in addition to that, all the relevant TypeScript code for the communication between the backend and the frontend is also generated for us. And the frontend bundle will be generated using a tool called Vite. And bundling the frontend is actually quite a complex process, but thankfully Vaadin takes care of it. So we don't have to think about things like dependencies, transpilation, obfuscation, minification, and so on. And this is actually good because the front-end bundle contains a lot of files, what we can see in this picture, by the way. So this picture is contained in every production build. When you're interested to see what kind of files are included, have a look at this picture. You might be surprised how much files there are. Per default, the production build results in an executable jar file that we can call a fat jar or uber jar. And as our Hilla app is based on Spring Boot, this jar file contains, as our Hilla app is based on Spring Boot, this jar file was created using the Spring Boot Maven plugin. And this jar file contains a lot of things. It contains the front-end bundle, it contains the compiled backend code, it contains all the necessary dependencies. And in addition, it also contains an integrated servlet container that serves our Hilla app as soon as this executable jar file is executed. This means that we only need a suitable Java runtime environment to run our Hilla app from this jar file, just like this command, for example. The production build of our Hilla app can also be built as a native image or created as a native image using GraalVM. And a Hilla app compiled as a native image is a standalone executable file, which means we don't need any Java runtime environment. So we can run it without a Java runtime environment. And compared to an executable jar file, a Hilla rep that was compiled as a native image is usually characterized by faster startup time and by less memory consumption. So to create a production build of our Hilla rep as a native image, we just have to add 2 more parameters to the Maven command we already know. And per default, the GraalVM compiler will determine the targeted machine type for the native image based on the current machine type of our machine. And this is no problem as long as we create and use the native image on the same or on a similar machine type. But if we, for example, would like to create a native image that we would like to run on a different machine type, we can add an additional parameter here. So using this parameter, for example, we can ensure that the native image will be compatible with most different machine types, for example. So the native image created, again, contains all the necessary classes, necessary dependencies, the front-end bundle, and of course, again, the integrated servlet container that serves our Hilla rep as soon as the native image is executed. So this means to execute our Hilla rep as a native image, we just have to run a very simple command line here. So the people behind Spring and Vaadin invested a lot to ship native image support, starting from Spring's ahead-of-time processing to using things like custom hints in Hilla, for example. So thanks to everyone who made this possible. It's very nice to be able to use native image support in Hilla. So let's move on to the deployment of our production-ready Hilla rep. So nowadays, I think applications are usually deployed based on containers. And I think this applies to deployments in public clouds, as well as deployments to on-premise cloud environments. And a production build of our Hilla rep can easily be used for such a deployment if we put it in a container. So let's have a look at a few Docker files. So this is an example of a Docker file we could use for our Hilla rep if we created the production build as an executable jar file. So we use a base image with a suitable Java runtime environment. We copy the production build of our Hilla rep into the container image. We expose the port of our Hilla rep, and we declare an entry point to start our Hilla rep as soon as the container is started. So actually, nothing new here. An executable jar file is very convenient for deployment, but it also has certain disadvantages, as you may know. Loading all the required classes from a nested jar file can take some time, especially when starting the application and when you have larger jar files. This can be avoided by unpacking the jar file, because loading classes from an unpacked jar file is faster and is therefore recommended for deployments in production. So this Docker file contains 2 stages. In the first stage, we copy the production build into the container image, and then we extract the jar file. We unpack the jar file, and we extract it, sorry. And in the second stage, we copy the extracted lib folder and the extracted app.jar file into the final container image, and then we configure the rest as seen before. Another option for reducing the start time and even reducing the memory consumption is the so-called class data sharing, or CDS, that was introduced in the recent Spring Boot 3.3 release, I think. And for this purpose, the Hilla rep is extracted and then executed once for training purposes. And the result of this training run is a file that is called app.jsa. And this file contains a dump of the internal representation of all the classes that were loaded when our Hilla rep was started. And this file, this app.jsa file, can be used like a cache for subsequent starts of the same Hilla rep. And therefore, we can copy this file into the final container image, and then we can reference this file at the entry point of our Docker file using a special JVM flag. All right, so based on one of the Docker files shown before, we can now create a container image using Docker or Podman, for example, and afterwards we can use the container image to start our Hilla app as a container. So pretty simple so far. Let's see how we can create a container for our Hilla app that was compiled to a native image. We start in a very similar way, but this time we use a very lightweight base image without a Java runtime environment because we don't need it for our native image. But what we also do is we copy the production build into the container image, we expose the port of our Hilla app, and we start our Hilla app as soon as the container is started. So this is very similar to the approach with the executable jar file. We can extend this Docker file to create the native image of our Hilla app in a separate build stage. And to do this, we need a suitable base image. But we are lucky because the great GraalVM community provides us a suitable base image for this. And after we copied all our project files into the build stage, we can then create the native image with the Maven command that we already know. And afterwards, in the second stage, we can just copy the created native image from the build stage into the container image of our final container and configure the rest as seen before. All right, so now we know how to create a production build and how a suitable Docker file for our production-ready Hilla app could look like. But when we think about shipping to production, we don't actually want to create the production build manually every time, and we don't actually want to create the container image manually every time. So therefore, it's time to automate things a little bit using continuous integration and continuous delivery. And yeah, as you all know, CI/CD systems play an important role in modern software development, and therefore I won't repeat all the benefits they deliver. But instead, I would like to show you how a simple CI/CD pipeline for our Hilla app could look like, because having a suitable CI/CD pipeline helps us to scale our development process and to be able to ship to production as often as necessary. And as you know, there are many different ways to implement a CI/CD system, and choosing the right tool depends on a lot of things. So if your workflow, for example, is centered around GitHub, you may choose GitHub Action to implement a CI/CD pipeline. Jenkins is another example that is often used in corporate environments, and there are many others, of course. But let's assume your company has its own Kubernetes or OpenShift cluster that you can use. And in this case, Tekton might be an interesting option for you. So Tekton is an open source framework for creating CI/CD systems, and it is part of the so-called, Continuous Delivery Foundation. And Tekton is around for 6 years now, and it has been used by well-known companies like Marriott, like the company who runs this hotel, IBM, and a company called Allianz. So you can install Tekton directly on Kubernetes like this, for example, or you can install Tekton on OpenShift using a so-called OpenShift pipelines operator. Using Tekton, we could set up a pipeline for our Hilla app that maybe looks similar to this. So each element in this picture represents a task, and a task can execute one or multiple steps, each in a separate pod. And the tasks can share a workspace to be able to operate on the same files. And we can choose from existing tasks that we can discover in a so-called Tekton hub, or we can implement our own task. Here you can see a Maven task from the so-called Tekton hub that we can use in our pipeline to create the production build of our Hilla app as a native image. And therefore, we need to configure this task to use a suitable container image that we already know. And we can configure the task to use all the Maven goals that we need in our Maven command, in this case, to create a native image of our Hilla application. So the next step in our pipeline would be to create actually a container image using the native image we just created and a Docker file like the one we've seen earlier. And for this purpose, we can create a so-called build config that we can implement in a custom task in our pipeline. So we can create such a build config with this command, for example, and this command, this OC command, belongs to the OpenShift command line interface. In the next step, we could pass this build configuration to OpenShift, and OpenShift will create a container image out of it using a tool called Builder. And we can even extend the build configuration to ensure that the container image is pushed to a suitable image registry once it has been created. So for now, our Hilla rep was built as a production build in the form of a native image. And we created a container image out of it using a suitable Docker file. And we also set OpenShift to push it to a container registry once it has been created. Everything automated in a very simple CI/CD system using Tekton. So the next step would be to use this container image and deploy it to Kubernetes or OpenShift. And what we could do here is we could use the newly released Vaadin Control Center because it simplifies the deployment and management of Vaadin applications in Kubernetes. And using Control Center, we could deploy our Hilla rep with a simple replica set that will serve our Hilla rep with a static number of pods. And this is actually perfectly fine, but for today we are going to look at a little bit more sophisticated deployment model. And when we think about choosing a suitable deployment model, we should remind ourselves that our Hilla rep comes as a native image with fast startup time and low memory consumption, and that is stateless by default, which means it can scale very well. And with this in mind, we could consider a deployment on Kubernetes or OpenShift in conjunction with the so-called horizontal pod autoscaler. This way, Kubernetes can start and stop additional pods of our Hilla rep based on things like CPU or memory utilization. And this is actually a good choice if our Hilla rep receives continuous requests 24/7. But as you know, most of our business apps are only used at certain occasions or during 9 to 5, for example, and most of the business apps are actually idle in the meantime. So what we could do with those apps? For those apps, a serverless deployment model can actually be a good choice. But what does serverless actually mean? Well, there is still a Kubernetes cluster with nodes and pods, of course. But this serverless deployment and the serverless deployment configuration will help us to set up a very simple deployment, which we will see in a minute. And in addition, it will help our Hilla rep to scale to 0. So in a serverless deployment model, our Hilla rep will only use resources in the cluster when users really want to use it. In the meantime, our Hilla rep can scale to 0, which means it won't allocate or use any resources in the cluster, which also means that the operational costs for our Hilla rep will be lower compared to a deployment model where we constantly allocate and use resources in the cluster. And what applies to one app makes even more sense when you have multiple or dozens of apps running on Kubernetes or OpenShift. Because keeping resources allocated for idle apps is actually quite inefficient, and of course it is expensive at the end of the day. But let's have a look how this serverless actually works. So this image is taken from a website of a framework called Knative. And this image shows the request flow in a serverless deployment model. And it all starts with a happy end user. So the user sends a request to our Hilla rep. And this way, a so-called HTTP router will notify an activator that there is a new request to our Hilla rep. And in addition, the HTTP router will forward our request to a queue so that it can wait there. And the activator will then tell the autoscaler that there is a new request. And the autoscaler will decide whether the current number of pods are sufficient to serve the requests or whether a new pod should be started. And once there are enough pods to serve the request is forwarded from the queue to a pod running our Hilla rep. And the queue regularly tells the autoscaler how much requests it contains. And this will allow the autoscaler to scale down the number of active pods whenever possible, even scale down to 0, so that there are no active pods running when there is no user that wants to interact with our Hilla application. So such a serverless deployment model can be implemented using a framework like Knative. Knative is an open source framework for serverless and event-driven applications. It can be used in OpenShift or in Kubernetes, and Knative serving, so this is Knative contains of multiple parts, and Knative serving is responsible for configuring a serverless deployment that we just discussed. So let's have a look at a very simple serverless deployment configuration using this framework, using Knative serving. So what we can see here is a very, very simplified configuration, but it's actually enough, and Knative serving will set up all the required components to enable a request flow that we've just seen in the picture. So it's a simple configuration, but behind the scenes, a lot of things are happening. So this means that this simple configuration is also enough that our Hilla rep will be scaled to 0 when it no longer receives any requests. If our Hilla rep receives a large or volatile amount of requests, we can extend this configuration to support scaling up. And we could use it by introducing a configuration parameter like this. This parameter controls the maximum number of incoming requests a pod can process before another pod is started. An alternative configuration could be to use something like requests per second here to decide whether a new pod should be started or not. Additionally, there's one thing we need to keep in mind here. The Knative pod autoscaler needs to know whether a pod is ready and healthy, and therefore we need to extend this configuration to include so-called readiness probes and liveness probes. And because our Hilla rep is based on Spring Boot, we can provide suitable endpoints for this using Spring Boot Actuator, as you may already know. All right, so our Hilla rep is now up and running. We have the production build of our Hilla rep compiled to a native image, running as a container in a serverless deployment model. Our build and deployment is automated using CI/CD, and our Hilla rep is running in an elastic and cost-efficient scaling using Knative serving. So I think we've done a good job so far, and nothing should go wrong now. But unfortunately, our Hilla rep is now served to our customers or colleagues, and this, of course, means that things will go wrong. And no matter how thoughtfully we developed our app or how good we tested it, because everything fails all the time. And I think you know that. And that's actually the reason why we should observe our Hilla rep. So observability, what does it mean? So observability is the ability to observe the internal state of a running application from the outside. And to achieve this, observability contains of 3 pillars that are logging, metrics, and traces. And I think most of you have a solid understanding how to observe a Spring Boot backend. That's maybe nothing new and easy for most of you. But what about observing a React front end? Has someone of you experience with observing a React front end? Anyone? Yeah, okay. Do you think it's easy? No. Okay. So let's have a look at both sides for our Hilla app, starting with the backend. So if we think about logging, traces, and metrics for a Spring Boot backend, I'm sure most of you have good ideas or opinions how to achieve this. And on the following slides, I would just like to give a brief example how we could do it using OpenTelemetry and Micrometer. So starting with OpenTelemetry. OpenTelemetry is an open source and vendor-neutral collection of various things. Its tools, SDKs, and APIs. And we can use OpenTelemetry to generate and collect and export telemetry data like logs, traces, and metrics. So exactly the things we are looking for. And fortunately, OpenTelemetry integrates very good with many popular frameworks and libraries, including Spring Boot and React, which makes it a good choice for our Hilla app. Java applications can use the OpenTelemetry Java agent without any additional code changes. And I think this is what Vesa showed us previously. I think you just added a Java agent to your configuration and didn't have to change anything. But as the Java agent does not support native images, we are going to look at the code-based instrumentation in the following examples. Micrometer, on the other side, is also open source and vendor neutral, and Micrometer provides a facade for many popular observability systems, and it allows us to instrument our JVM-based applications. And I think Micrometer and OpenTelemetry complement each other quite well and are therefore a good combination for observing our Hilla app. So let's start with the first pillar. Let's start with tracing. So tracing helps us to understand the request flow in our Hilla app, starting from an HTTP request to method invocation in the backend down to things like database queries, for example. And trace IDs and span IDs play an important role in this context as they help us to identify corresponding actions. We can implement tracing in our Hilla app using Spring Boot Actuator and Micrometer tracing. And to get started, we need to add some dependencies to our Hilla project. Fortunately, Spring Boot Actuator provides a very good auto-configuration for Micrometer tracing. This means, among other things, that Micrometer tracing will provide trace IDs and span IDs as so-called MDC attributes, which can be helpful to combine things like traces and log statements, for example. And to be able to export all the traces to a suitable trace backend, we are going to bridge the traces to OpenTelemetry, and then we are going to export them using a suitable exporter. And this exporter will use the so-called OpenTelemetry protocol, or OTLP for short. And afterwards, we can configure the tracing. And per default, Spring Boot will only sample 10% of all the requests to prevent overwhelming the trace backend. We can change this property to, let's say, 100% so that every trace is sent to the trace backend. This can be helpful during development or when we are just starting to explore things, for example. And of course, we have to set an endpoint to a trace backend to whom all the traces will be exported. By the way, in this slides and this examples, I'm using a trace backend that is called Signos. It's maybe fairly new. It's an open source Datadog alternative. So the screenshots you are going to see, they are based on a tool called Signos. So with this tracing configuration in place, all the default traces will be exported to our trace backend using the OpenTelemetry protocol. And this means that in our trace backend, we can see all the HTTP requests from the Hilla frontend to the Hilla backend, for example. And for every trace, we can see details like the trace status, and as well as associated metrics like the duration, for example. And in addition to that, we can use the so-called Micrometer Observation API to create custom spans to observe custom functionality in our Hilla app. So in this simple example, we are just going to wrap a custom span around a method call of a Spring Data repository. And doing this, we are then able to see in our tracing backend how this works together. So in our tracing backend, we can then analyze this custom span together with other spans. So here we can see an HTTP post request from the Hilla frontend to the Hilla backend and our custom span as a child operation of it, both together with associated metrics like durations, for example. Let's move on to the next pillar, which is logging. I think logs play an important role in observability because they can contain a lot of valuable information. And therefore, we want to collect and export all the log statements of our Hilla app, especially in this case, our Hilla backend, because we are still on the backend. And for this purpose, we are going to use a log appender. And this log appender will bridge all the logs from logback into the OpenTelemetry SDK. And therefore, we need to add a dependency to our POM-XML in this case. And afterwards, we need to extend our lockback configuration to use this OpenTelemetry appender. We tell the appender to capture MDC attributes like trace IDs and span IDs that micrometer tracing provides for us. And this will help us later to combine traces and log statements. And if we don't want to use lockback, there is an alternative appender for log4j, for example. And finally, we need to initialize the OpenTelemetry SDK in our app because we don't use the Java agent because we have an example with a native image here. And as part of this initialization, we are configuring a so-called log record processor in conjunction with an exporter. And the goal is just to export all the log statements to a suitable backend using the OpenTelemetry protocol again. And then, in a suitable backend, we are able to discover and query all the logs of our backend application. And we can do things like create alerts based on the logs, or we can create dashboards, for example. And what we can see here in this screenshot, again, this screenshot is based on a backend called Signos. We can see all the logs of our Hilla backend here. And in the details of a log entry, we can of course see the name of our app, the actual log message, as well as the trace ID and the span ID that was read from MDC. Okay, let's have a look at the last pillar, which is metrics. Metrics are helpful to monitor our application. And Spring Boot Actuator provides auto-configuration for micrometer metrics. And having a dependency like this in our class path is actually enough, and Spring Boot will configure a required registry. And in our case, we want to export the metrics, again using the OpenTelemetry protocol, and we want to export all the metrics to our backend, and therefore we need to configure the URL to our metrics backend to whom all the metrics will be exported. Unfortunately, Spring Boot Actuator provides metrics for a wide variety of technologies right out of the box. So in this screenshots here, for example, you can see JVM metrics for things like memory usage, thread utilization, or the number of loaded classes. These are things that are there out of the box, and we can just observe those kind of metrics. Another example are metrics for popular things like Hibernate, JDBC, or Spring Data, for example. So these dashboards, they just show things like the number of executed queries, the number of idle and active JDBC connections, or the number of total and successful invocations of a specific Spring Data repository. So these kind of metrics are available out of the box when we combine Spring Boot Actuator and micrometer tracing. So that's it for the back end. That was more or less the easy part. Let's have a look at the front end. So how can we observe the React front end of our Hilla app? Observing a web front end is actually quite challenging because the browser is not under our control and it is very far away from us. But nevertheless, it is pretty important to know what is going on in the browser and how our users perceive our application. And therefore, we should have a look how to collect logs, traces, and metrics in the browser to get a better understanding of what is going on in the front end. So if we take a look at the documentation of OpenTelemetry for JavaScript in the browser, we will unfortunately find this warning here. So everything we are going to see now is a little bit of work in progress and may be subject to change. So it's still in an early stage of development. Not all aspects of it, but some of the aspects. But nevertheless, I think it is also still interesting to see what is already possible and how it can help us today. So let's start with tracing again. First of all, we need to install some dependencies and set up an instrument OpenTelemetry in the front end of our Hilla app. And next, we need to set up the OpenTelemetry SDK for our Hilla app, especially in this case for the front end. And this includes several steps, and I would just like to highlight a few of them. So first of all, we need to configure a so-called trace exporter that will export the traces that we are going to observe in the front end to a suitable backend. And again, here we are using the OpenTelemetry protocol. So this is actually more or less the same from a conceptual point of view when we think about the back end and how we do it in the front end. And in addition, we configuring a so-called propagator. And this propagator is actually very important because it opens the door to a thing called distributed tracing. So in this case, the trace ID is created in the browser, in the front end, and it is sent to the backend in a suitable HTTP header. And then the backend will use this trace ID for subsequent calls and method invocations. And this allows us to see front-end spans and back-end spans under one trace ID. And this can be very helpful to understand how the request flow through our application is actually working, starting from the front end, going all the way to the back end. One last thing is we could add a couple of so-called auto-instrumentation that are specific to web front ends. And with this in place, we get a lot of information about what is actually happening in the browser. Like, for example, when a user clicks a button or when a user navigates to a specific view. I don't want to go into the details here. I just wanted to give you an impression what it means to add this auto-instrumentations. And here we can see an example in our backend. So this is again our Signos backend where we can see all the traces and can analyze them. And here we can see front-end and back-end spans that are collected under one trace. So what we can see here is we start with a navigation in the front end. This is the first red arrow. And then we see subsequent actions that are happening below, like, for example, the custom span that we wrapped around the method call of our Spring Data repository. And we can see how these align to each other and how they are corresponding, again, associated with metrics like the execution duration, for example. So let's move on to the next piece, which is logging. And unfortunately, the OpenTelemetry Logs API and SDK is currently still under development. So it's not yet available and there's nothing to show yet actually. But fortunately, there are ways to get some information from the front end, especially when things go wrong. And one of the ways could be to wrap our front end in a so-called error boundary to handle errors in a convenient way, and especially to handle unexpected errors in a convenient way. And because our Hilla wrap is based on React, our Hilla wrap is based on React in the front end, we have a rich ecosystem of ready-made components for this purpose to choose from. And in our case, we will just install this npm package that is called React Error Boundary. And then we can use the provided error boundary component in our React app. This means we can wrap this error boundary component around our Hilla wrap, just like this, for example. And as you can see, this error boundary component has this property called onError, and there we specify a logError function. And this is how this logError function could maybe look like. So in this logError function, we use a tracer, and this tracer comes from our OpenTelemetry SDK that we configured for the React front end of our Hilla wrap. And using this tracer, we create a custom span. And within this custom span, we then record the exception together with an error status as well as the error message. And this way, we are able to collect all the error information that occur in the front end and then export them to our backend. So in a suitable backend, again, we can see all the errors that occur in a React front end. And then we can analyze all the errors in our suitable backend. So in this case, for example, we see things like the error message as well as the trace ID. And maybe you've seen, the stack trace. And maybe you've seen the stack trace when you worked with Hilla or React. It's a not very helpful stack trace, but it is a stack trace at least. And this is what we can see in our tracing backend. So although the user is far away, we can still see the error that the user saw on the browser. And I think this can be very helpful when we try to support the user. Okay, let's look at the last pillar of observability for our Hilla frontend, which is metrics. Using the OpenTelemetry JavaScript API and SDK, we could create custom metrics like counters or histograms, for example. But instead of custom metrics, I would like to show you a set of ready-made metrics that are called Web Vitals. Web Vitals is an initiative by Google that provides metrics that can help us to measure the user experience in a web frontend or in a web page. And I want to show you one Web Vital as an example to get a better understanding of what Web Vitals actually is. So this is LCP. LCP stands for Largest Contentful Paint, and LCP tries to measure the perceived load speed of a web page. And therefore, it marks the point in the page load timeline when the users or when the page's main content has likely been loaded. And to provide a good user experience, sites should strive to have an LCP of 2.5 seconds or less. So this means the main content of the page should have been loaded within 2.5 seconds or less. So then this way, Google would assume this is a good user experience. So to check whether our Hilla frontend has a good LCP, we can use this Web Vitals metrics together with the OpenTelemetry setup in our app. And before we can do that, we have to install some more dependencies because we are working with React in this case. We can then extend the existing OpenTelemetry setup for our React frontend. And what we do here is we send the metrics to our metrics backend using a suitable exporter. And again, we are using the OpenTelemetry protocol here again, which is actually the baseline for almost every kind of export operation we do here. And then we initialize a so-called meta provider. And this meta provider can be used to observe this LCP metric for every view in our Hilla frontend. And with this configuration in place, we can then head over to our metrics backend, and then we can analyze the metrics, in this case, the LCP metric. And what we could do is we could create a dashboard, for example, to see whether the LCP for our Hilla frontend is good or not. And we could even create something like an alert to get notified when the LCP of our web frontend is poor over a longer time period. Okay, let's do a quick recap here. So we saw how we can implement observability for the Hilla backend, and we saw how we can implement observability for the Hilla frontend. In both cases, we used OpenTelemetry, but in the backend, we also used micrometer tracing, and in the frontend, we used an error boundary component and this thing called Web Vitals. With this in place, we can see logs, traces, and metrics for our front end and our back end, and we have this thing called distributed tracing in place, which can be very helpful to understand what is going on from the front end to the back end. So now that we have all this data in place, we should think about, or we should take a moment to think about what we would like to do with all this data. So when we are testing our application, it's perfectly fine to have all this information available because we want as much information as possible. So actively analyzing logs, looking at traces and metrics can be helpful to identify bugs or to find performance issues. During a hypercare phase, we could use things like alerts to get notified when errors occur that we may want to fix quickly. But what about regular production? Most of us don't want to get mail alerts for every error that occurs in production. And actually, we don't like to look at metrics all the time to ensure that our app runs as expected, for example. And this is even a bigger problem if we have multiple apps in production or massive traction on one of our apps. So in this way, or in this case, all the available information, all the available observability information can quite become very overwhelming. But with all the data and all the tooling in place, we could actually enter a field called site reliability engineering that may help us to deal with this in a better way. So site reliability engineering, or SRE for short, is around for almost 20 years now, and it's definitely worth to take a look at it if you not already haven't. I won't give you an introduction to SRE here, but I would like to highlight some aspects that are related to observability. Let's start with a thing called service level indicators, or SLI for short. An SLI is a metric over time that informs us about the health of a service. So a service level indicator tries to describe things like availability, latency, or quality of a service from a user's perspective. So this is important, it's described from the user's perspective. And an example of an SLI for our Hilla app could be our main view should load quickly. So this is not very precise, but it is an SLI in the sense of SRE. And a service level objective, or SLO for short, is another thing. And a service level objective describes how often a service level indicator must be met. So they both relate very strong together. And an example of an SLO for our Hilla app could be 95% of all the requests to our main view should have a good LCP over a 28-day window, for example. So this is a very precise service level objective, but there's one interesting thing here. We are not striving for 100%. We are not striving for 100% because often it is not necessary, or it's just impossible to strive for 100% because everything fails all the time. And therefore, SRE has a concept called error budgets. And error budgets describe how much failure a service is allowed to have. And if we define a service level objective for our Hilla app, an error budget is a byproduct we can use. It tells us how much failure is acceptable. And if our app operates within its error budget, we don't have to look at every error that occurs. Instead, we can focus on nice things like building new features and shipping new features to production. But if our app runs out of error budget, then it's definitely time to investigate. And then we can use all the logs, traces, and metrics that we have available in our backend, especially in our tracing backend. Because running out of error budget most certainly means that our users perceive some kind of service degradation that we definitely have to deal with. All right, so I think it's time to come to an end and to summarize the talk. So we've seen how we can build our Hilla app as a production-ready artifact using the production builds and using GraalVM to create a native image. We discovered how we could create suitable container images for our Hilla app. We saw a simple example for a CI/CD system using Tekton, which can help us to build and deliver our Hilla app in an automated pipeline. We talked about serverless deployments, and we saw how we can operate our Hilla app in an elastic and very cost-efficient way. We had a look at the current state of observability for the backend and the front end of our Hilla app. And finally, we briefly explored some common SRE concepts that can help us to leverage all the collected observability data so that we can be sure that our Hilla app is delivered in a suitable and reliable way. So that's it. I know it was a lot, but do you have any questions? Okay, yes, okay, thank you. Then thank you very much for your attention. Thank you, Vaadin, for having me here, and enjoy the rest of the day.